My name is Twin Tran, and I teach 8th grade science at Powell Middle School. Go Panthers! I am so happy to be here with you today. This week is week 6, and I will be presenting to you a lesson for 8th grade science. You can find all activities for KCS at home on the KCS website. Under the Student Resources tab, just look inside the Week 6 packet. If you need a printed copy of these materials, they are given out at the meal distribution sites on Wednesdays from 10 a.m. to 12 noon. This week, we are going to be talking about Standard 8.ESS 3.2, which just states that students will be able to collect data, map, and describe patterns in the locations of volcanoes and earthquakes related to tectonic plate boundaries, interactions, and hotspots. So let's get started. If this video is hard to understand, you can turn on closed captions if available, adjust the playback speed to slow down the video, consider watching short clips, then pause, listen, and watch again, and then ask someone in your home to watch the video with you. Stop frequently and talk to your partner about what you heard and understood. Did you know that there are earthquakes in East Tennessee? Earthquakes in East Tennessee are common, but we don't always feel them. You may have felt the earth move on January 20th, 2020. I know that my students were really excited to talk about the earthquake the next day in class. If you didn't happen to feel it, it may be because it was only a magnitude of 3.8 on the Richter scale. And if you look at this chart in the bottom right corner, you can see that falls under the minor category. I myself did not feel the earthquake on the 20th, and I was very disappointed. So if we can have earthquakes in East Tennessee, what exactly causes them? Why does the earth move? In some instances, the earth moves due to plate boundary motion. This is caused by convection currents in the earth's interior. So as you recall from your earth science module, the earth's crust is broken up into several large plates, and they sit on the earth's mantle, which is molten rock, and that molten rock is heated and cooled as it sinks and rises in earth's interior. That sinking and rising motion are the convection currents that move the plates a lot like a conveyor belt would. This movement causes the tectonic plates to be divided, like right here. They can slide past each other, which isn't really evident in this particular diagram, or they can collide or move toward each other. So what happens when the earth moves? There are several types of boundary motion. The first one that we can see here are divergent boundaries. And lots of things are going on in these pictures here. I have two animations for you to look at. On the right side here is continental crust, and on the left side over here is oceanic crust, and you can see with these arrows that the crust is moving away from itself. It's being divided because of the convection currents underneath are pushing them apart from themselves. For oceanic crust, this leads to seafloor spreading, which you studied in week 2 or week 1 of KCS at home. And then over here on the right hand side with continental crust that's being divided, we get rift valleys. That as the continental crust is being divided, it kind of sinks down a lot like taffy or caramel. Sometimes the convection currents cause the plates to move past each other. Instead of running into each other or moving away from itself, they just slide past each other going in opposite directions, kind of like passing someone in the hallway. This typically only leads to earthquakes. There's no other real activity that occurs with transform boundaries. Just earthquakes happen, and the most well-known fault here for us in North America would be the San Andreas Fault in Southern California. Keep in mind, though, that earthquakes can occur at all types of plate boundaries, but specifically at transform boundaries, that's the only thing that happens. When pieces of Earth's crust move toward each other, we call those convergent boundaries. And again, we have a lot going on in this picture. Let's start over here in the top right side. In the top right side, we have two pieces of continental crust that are colliding. When these two pieces of continental crust collide or push towards each other or move towards each other due to the convection currents underneath, basically what you're going to get are folded mountains. The Earth folds in on itself and it rises up and we get mountains. On the bottom half of the screen, we have a lot going on. In both of these, we have oceanic crust involved. On the right-hand side of the screen, you have oceanic and oceanic crust that's coming together. When two pieces of oceanic crust collide, the more dense piece of crust, or typically the older piece of crust, is going to be pushed under the newer crust. Same thing's happening over here. Oceanic crust is more dense than continental crust, so it is being pushed under. In both of the places where it's being pushed under, those are called subduction zones. And in a subduction zone, the crust heats in Earth's interior, sometimes even melts. When it melts, these pockets of magma rise up through the crust that it's been pushed up underneath and eventually break through and form volcanoes. On continents, that would result in volcanic mountain ranges. In the ocean, that would result in volcanic island arcs. So in summary, the Earth is shaped by tectonic plate motion. Just the topography of Earth, the way Earth looks, is due to the movement of the tectonic plates. That could be seafloor spreading, that could be rift valleys, that could be continental mountain ranges, that could be volcanic mountain ranges, and even volcanic island arcs, right over here. All of this is just a little bit of background knowledge so that you're prepared for today's actual goal. Today, your success criteria will be that I will know I am successful when I can identify patterns from volcano and earthquake data to make predictions and relate it back to Earth's plate boundary motion. So identifying patterns and making predictions and even relating things back are all science skills that we work on every time we're in science class. So the scientific practice of identifying patterns is a skill we will work on today. You will be using data from earthquakes and volcanoes to identify a pattern in their distribution and relate it back to Earth's plate boundary motion. So, do earthquakes and volcanoes happen just anywhere, or is there a pattern to their distribution? That is the answer we'll be looking for today. In your packet, turn to the science section and find the first page for today's activity. Pause the video and read the introduction and procedures. Now that you've finished reading today's introduction and procedures, let's take a look at step 1 and 2. Step 1 and 2 ask you to make predictions about where you think earthquakes and volcanoes occur. For me, I might predict the Hawaiian Islands, Japan, and the Caribbean for volcanoes because I've heard of volcanoes being there, although I've never seen them. I think back to pictures that I may have seen, even though I've not visited any of those places. For earthquakes, I think back to what I've heard on the news. Obviously, I think of the earthquake that we've had here in East Tennessee. I think of major earthquakes that have occurred in Southern California. I think of Haiti. I think of Italy. What places on Earth do you think of when you hear the words earthquake or volcano? Think about those places and plot those on your map as predictions if you think that's where most volcanoes and earthquakes occur. Now that you have made your predictions for steps 1 and 2, let's move on to steps 3 and 4. One skill you'll need to have in order to be successful today is the ability to find locations given longitude and latitude. Down at the bottom of today's activity sheet, you can see a chart that lists coordinates for several volcanoes and for several earthquakes. Recall that in order to use those coordinates, you must know longitude and latitude. Longitude are lines that run north to south. Those are the vertical lines on a map, but they measure east and west from the prime meridian. Latitude lines are your flat lines on a map. They run east to west, but they measure north and south from the equator. So looking at today's activity for steps 3 and 4, you're going to be using red and green colored pencils in order to plot the volcanoes and earthquakes that have occurred here on Earth using the coordinates for longitude and latitude from the earthquake table. The first one has been done for you. It may be hard to see, so we're going to work through them together as well. So the first set of coordinates for a volcano is at 150 degrees west and 60 degrees north, and you can see that I've already starred these on our screen here. So for 150 degrees west, we look over here, this is 0, this is your prime meridian, and we're going to move west. So we have 20, 40, 60, 80, 100, 120, 140, and then 160 degrees west. So 150 is going to be right in between 140 and 160, so that's why my blue star is there. For 60 degrees north, we find our equator here at 0, and we're going to move north, 20, 40, 60, and there's my blue star. So in order to plot those 2 points, you're going to see where do the blue stars meet. And right here with my red star, we can see that there is a volcano somewhere in Alaska. We're going to do the same for our first set of earthquake coordinates. So again, the first set is 120 degrees west. So 0, 20, 40, 60, 80, 100, 120 degrees west. There's my blue star. And then 40 degrees north, again 0 for the equator, 20, 40 degrees north, blue star. And then where do these two things interact or intersect? Right here. That looks like maybe Washington State, somewhere up there. Maybe even just in California. It's kind of hard to tell without any state outlines. But there's my green star representing an earthquake that has occurred at some point in Earth's history in that location. So now you can pause your video and plot the remaining points, and also complete procedure steps through 6. So once you finish plotting the steps for step 3 and step 4, you're going to look for a pattern. Can you find a pattern? And once you find that pattern, you're going to label it the Ring of Fire. So let's take a minute and look back at our success criteria. I will know I am successful when I can identify patterns. Were you able to find a pattern from volcano and earthquake data to make predictions? We haven't gotten to the prediction part, but we will in just a minute. And we'll also relate it back to Earth's plate boundary motion. So on the next part of your packet, you have some analysis questions. In order to answer those questions, I want to look at these two maps. On the left-hand side of my screen, I have this red circle. I think in your paper it might be yellow, but we have this red circle that indicates generally where you can find earthquakes and volcanoes occurring here on Earth. On the right-hand side of your screen, I have a map of the tectonic plates all over Earth. Notice that at some of these plate boundaries, we have arrows. Sometimes they're pointing toward each other, sometimes they're pointing past each other, and sometimes they're pointing away from each other. And that's going to indicate whether it's a convergent, divergent, or transform boundary. So your first analysis question was, what do you notice about the location of the Ring of Fire? So let's backtrack. I've lightened up these two maps so I could overlay one over the other, and you'll notice that the ring that I have labeled as my Ring of Fire matches up right here because I lined up North America and Europe and Asia, and you can see that the Ring of Fire kind of follows a little bit this boundary right here around the Pacific and the Nazca Plate. What types of plate movement occurs in the Ring of Fire? So if we look back at that picture again, you can still see, look at that red circle and compare it to some of the arrows that you see there. What kind of plate boundaries are occurring in order to result in these earthquakes and volcanoes? From there, I'd like for you to try to explain the relationship between volcanoes and earthquakes and the Ring of Fire. Is there a relationship between volcanoes and earthquakes? And what do they have to do with the Ring of Fire? Why might we have more earthquakes and volcanoes along the Ring of Fire than anywhere else on Earth? Look closely at those arrows that I pointed out to you on your tectonic plate map and draw some conclusions from those arrows. Next, part of our success criteria was being able to predict based on the data that we have. Scientists can't predict exactly when an earthquake will occur, but if you were to try to predict the location of the next earthquake, what would you answer? In general, where do you think that could happen? And finally, I want you to think about the earthquakes that we have here in East Tennessee. We do sometimes experience earthquakes in East Tennessee, but we're not near a plate boundary. But the earth is still moving. Those convection currents are still occurring underneath the crust that we live on. Given the fact that we do have some convection currents underneath East Tennessee that sometimes results in earthquakes, why don't we have volcanoes? Thank you so much for your time and attention this week for week 6 of Science and KCS at Home. I hope you have a wonderful summer. I miss you guys. I miss all of my students, and I can't wait to see my new students next year.